Good morning, class. We are looking at calculus 1 exam 4 review covering 4.7 to 4.9 and 5.1 to 5.5 and 6.1. Here's part 1. We are going to cover 4.7 and 4.8. 4.7 is optimization problems. 4.8 Newton's method. So here's chapter 4, what is left of it, optimization problems, Newton's method, antiderivatives. Here's chapter 5, integrals or anti-differentiation, areas and distances, the definite integral, the fundamental theorem of calculus, indefinite integrals, and the net change theorem, the substitution rule. Chapter 6 is about application, and we're going to cover 6.1 for this exam. And again, we start reminding everyone of all the differentiation formulas we've seen, okay, from the basics to more interesting ones involving tangent, cotangent, trigonometric functions, inverse trig functions, so on and so forth. All right. Optimization problem, the concept is about how to maximize and minimize things. For example, you want to maximize profit, you want to minimize cost. So here's some examples. We want to find two numbers whose sum is 54 and whose product is a maximum. So first you have to define your variables, the two numbers. You're going to say, let's say, x and y. You have an objective function that is going to maximize the product of x times y. And you have a constraint, the sum must be 54. That means x plus y is 54. This is the limiting fact, as an example. If 5400 pi square inches of metal is used to construct a cylindrical storage drum, what is the maximum possible volume? We need a piece of information from geometry. So here's a cylindrical shape. We want to maximize the volume. The formula is pi r squared h. And it's subject to the surface area because we want to look at the material, right? This much. The surface area would be the area of the bottom times 2, pi r squared times 2 is 2 pi r. And the surrounding, the circumference times the height, 2 pi r h, and that is 5400 pi. And you take it from there. It is important to translate the problem. You have to have the drawing, you have to define your variables, you have to come up with two equations, the objective function and the constraint. Here's another example. A farmer wants to fence a rectangular field beside a river with 2,400 feet of fencing. The river itself will be one of the four sides. What dimensions will give the largest area? Again, the drawing. First and foremost, you have a drawing like that, and you define your variables. The x represents the width, y represents the length, a represents the area. Your objective function is to maximize the area, which is x times y. And the constraint is 2,400 feet of fencing. Normally, the perimeter is 2x plus 2y, but the way this is set up is 2x plus only 1y because one side, we don't need the fencing, and that's 2,400. So as long as we have these two, that means translation of the question, we are ready to move on. A is a function of two variables. To make it a function of one variable, we always go to the constraint and we solve for one of those variables. If I solve for y, I get 2,400 minus 2x. And if I put it into this, now A becomes a of x. You can literally change this to a of x. It's a function of one variable. And it gives us this open interval of 0 to 1200. This is important. And why is that? First of all, we are talking about dimensions. It must be positive. Why 1200? If you set this one equal to 0, x becomes 1200. And if you choose x to be larger than 1200, the parenthesis becomes negative times positive. The area becomes negative. We can't have it. Therefore, we have the open interval of 0 to 1200. And we distribute the x for the sake of the next part because we are going to find the CP. A prime differentiation gives us 2400 minus 4x. The reason we set it equal to 0 because we are looking for CP, critical points, and there's only one of them, x equals 600. Now, before we move on, remember whether we do the first or the second derivative test, if we happen to have an open interval with one critical point, the first or the second derivative test, they tell us it's a local max or mean. However, since it's only one, it becomes an absolute. So since it's only one, we already know it becomes an absolute. It is easier to use the second derivative because if I go with a double prime, I get -4, which is independent of x. If it's not, I have to plug in 600 and it makes no difference. This is negative, which means it's concave down. So when it's concave down, looking like that, means the maximum occurs at x equals 600. So you plug it back into this constraint or to this one to find the y, which becomes 1200. So the dimensions are 600 by 1200, which gives us the area of 720,000 square feet. So again, in short, optimization problems, you're dealing with word problems. You have to define your variables. You have to have a drawing that makes sense. A box with a square base and open top must have a volume of 32,000 cubic centimeters. Find the dimensions that minimizes the amount of material used. Well, reminding everybody about some basic geometric formulas. You have a rectangular solid, and the volume is the width times the length times the height. The surface area, you calculate each side and you multiply it by 2. For example, the front is the length times the height. The side, this is width times the height. And the bottom is length times the width. As you can see, we have 2 of each. That's why we have this number 2. 2 times W times L plus H times L plus H times W. That's the surface area. If we happen to have a cube where all sides are equal, the volume is S cubed. One face has area of S squared. There are 6 sides, 6S squared, just to remind everybody. Now, in this case, we want to find the objective function, which is minimizing the surface area. Why the surface area? Because we want to minimize the amount of material used. And normally, as you look at this one, this is X, this is X, this is H. So all the walls would be 4XH. Normally, we have X squared at the bottom, X squared at top, so plus 2X squared. But this is an open top, only 1X squared. So minimize the surface area, which is 4XH plus only 1X squared because it's open top. Otherwise, it's 2X squared. Subject to the volume is supposed to be 32,000 cubic centimeters, which is X squared times h. This is understanding the problem and translation of the problem. Now, what do? Almost always, we go to the constraint and we solve for one of the variables, because when we look at the objective function has two variables, namely x and h. So if you solve for h, you get 32,000 over x squared. You replace the h in this formula with 32,000 over x squared. This goes away, and this changes to x. And then when you multiply 4 by 32,000, you get 128,000. So we have 128,000 over x plus x squared. Now, for the sake of differentiation, we're going to write the first one as 128,000 x to the power of minus 1. And x is positive because x represents dimensions. There's nothing else there, so it's just positive. We don't have any other restrictions. Now, to differentiate this, we're going to use this one. 128,000 times negative 1 makes it negative 128,000 x to the power of minus 2 plus 2x. Remember, we are looking for critical points, which means we are going to look at where f prime, in this case, s prime is 0 and where it doesn't exist. So we are going to write it as over x squared minus 128,000 over x squared. We take a common denominator of x squared, and 2x changes to 2x cubed. A fraction is 0 when the numerator is 0. So s prime is 0. That means the top is equal to 0. And this one we can easily solve, because 2x cubed is 128k. X cubed is 64k, and x becomes 40. Now, what I want to add is, when you're looking for a critical point, you said the top equal to 0, you said the bottom equal to 0, where f prime, or in this case s prime, does not exist. And when you set this equal to 0, x becomes 0, and that's not part of the domain. We don't have to worry about that. Speaking of the domain, we can write this in the interval format. So we have an open interval. We have only one critical point. So whether we do the first or second derivative test, and it's going to give us a local mean or max, it means it's absolute. That's the meaning of that. So with that being the case, we go with second derivative test. So we go with s double prime, and to go with s double prime, we're going to use this one, is easier. Minus 128,000 times minus 2. Their product is positive 256,000 x to the power minus 3 plus 2. Now the second derivative test says plug in the x and look at the sign. Is it positive or negative? If we plug in 40, first of all, this is 40. Let's see what happens. I hope you see why it's positive. Because if I plug in 40, I get 256,000 divided by 40 cubed plus 2. And again, notice, you don't even have to evaluate this. This is some number which is positive. Plus 2 makes it even more positive. We just want to know if it's positive or negative. Needless to say, you can actually calculate it. But I'm interested in the sign. It's positive. That means concave up that means minimum, because concave up looks like that. Let's do the drawing here. Concave up looks like that. And the minimum occurs at this point when x is 40. So what is h? Well, if x is 40, we have 40 times 40. What is h? You can go to this formula and divide by x squared, or 40 squared. In other words, you can use this formula, and that gives you h equals 20. So I'm going to assume everybody can calculate that. So the dimensions are 40 by 40 by 20. And we are done. They just were asking for the dimensions. However, if we wanted to find the surface area, we would plug in the values. And it gives us 4,800 square centimeters. What is the minimum distance between the two functions? They happen to be parabolas. One is y equals x squared plus 1. That means y equals x squared. Move it up by 1. And y equals x minus x squared. Of course, this is minus. It flips over. All you have to do, find the vertex x equals minus b over 2a, a couple of, intercepts, graph it. I'm assuming we are okay with the graphing. So the graph looks something like this. Very straightforward, and I hope, again, nobody has any problem with the graphing. So we have the graph. The minimum distance happens somewhere between those 2 points. This one has coordinates x and y, comes from this y. This one has the coordinates x and the y comes from this one. It's a vertical distance that would make it the smallest distance. This is the distance we are looking for. So we are interested in this vertical distance, v of x, which is the y coordinate of the top minus y coordinate of the bottom. And so we want to minimize this. By the way, we distribute, this becomes minus x minus x plus x squared, and it simplifies to 2x squared minus x plus 1. X can be anything, so in an interval format from negative to positive infinity. Now let's do differentiation, v prime of x, because we're interested in finding CPs, critical points. V prime is 4x minus 1. And the reason we set it equal to 0, because we are looking for all the critical points. X becomes 1/4, and there is only one critical point. So we have an open interval, we have one critical point, and it makes it not only local, also an absolute. Minimum or maximum, we don't know yet. So we have to look at v double prime and a plug in. V double prime of 1/4 is positive. I'm going to get you started with that, and then you can finish it later on. So here's v prime and v double prime is just 4, and it's always positive. Now you have to plug in 1/4, but there is really nothing you can do here because it's a constant. Okay, v double prime of, it's important to know it has to be plugged in, but v double prime is independent of x, so it's always 4, it's always positive, it's always concave up, and therefore it's minimum. When it's concave up looking like that, we have the minimum. Let's just to the drawing. Looking like that. And so the minimum occurs when x is 1/4. So what is the minimum? We plug in 1/4 into this one or into this one. If you go through the process, it might be easier to go through this one because 1/4 squared and minus this one is 1/4 squared and another 1/4 squared, 1 minus that, and you end up with 7/8. So what is the minimum distance? This is what we need to answer, okay? This is what they want us to answer, okay? And the answer is the minimum distance between the two is 7/8, and they haven't given us any units, so we don't have any units to give back, okay? A cylinder is inscribed in a cone with height h and base radius r. Find the largest possible volume of such a cylinder. Again, I can't emphasize the importance of drawing and showing your readers what you're doing, because to me, it makes no sense otherwise. So we have a cylindrical shape inscribed in a cone. So looking like that. That's the first thing we do. Now we are going to define our variables. Well, we say this is x, this is y. They said this is r, and this is h. So the height of the cone is h. The radius is lowercase r. And we are going to go with x and y. This distance is y, this distance is x, and I'm going to go with a couple of things to explain to you what happens here. So if we call capital H the height of the cylindrical shape, capital R the radius of the cylindrical shape, couple of things we should know. Again, the information from geometry, the volume is pi r squared h for the cylindrical shape, because we are looking for the volume. And according to this, this is equal to x, and h is equal to the lowercase h minus y. So take a look at this important information. If this is x, that's the same as r, because this is the radius of the cylindrical shape. If you call this distance y and the whole thing is h, h minus y becomes the height of the cylindrical shape. So you have to define your variables accordingly, and your variables may be different. It doesn't matter as long as it's there. More power to you. So the volume is pi r squared h. So what do? We change the r with x and capital H with h minus y. So we put this into this formula, and v becomes pi x squared times the parentheses h minus y. And it's important to know that on the right side, h is fixed because it's the height of the cone. X is changing because depending on, what happens here, we could have a shorter one, okay, or a taller cylindrical shape. The y also is a variable and it changes. So what do? If we look at this part, if you look at this part, it's the following triangle. We made it larger. This distance is x, this distance is y, this distance we call it lowercase r, this distance is h, the height of the cone. And as you can see, the corresponding angles are identical. This is in common. These two are the same. These two are 90 degrees. So the two triangles, the small one. So first of all, we use this one, okay, class? We use this. The small one versus the whole thing, the large one. They are similar triangles. And similar triangles, remember, corresponding angles are identical, corresponding sides are in proportion. So for example, I can pick this side, x from the smaller one over r from the larger one is equal to this side, y from the smaller one, and the whole thing, h from the larger one. The reason I do that, because with the cross product, I can solve for one of those variables, either x or y. It's easier to solve for y. And I hope you realize this means ry equals xh, and y is xh or hx over r. And now we are going to replace it here. And v, the volume of a cylindrical shape, which is a function of two variables, x and y, with that becomes a function of one variable. So let's change the y. Multiply it, and x is between 0 and r, and there are many ways to do the interpretation of that. First of all, x is a dimension, can't be negative, it can't be 0, because if it's 0, then we don't have a cylindrical shape. If it's equal to r, then there is no cone, it becomes all cylinder, and it's impossible. The other way is that if you set this one equal to 0, if you set this one equal to 0, that you see that x has to be less than r. So x is between 0 and r, clearly less than r. So again, you can just go with that. Or like I said, x represents a dimension must be larger than 0 if you set this one equal to 0. Okay. Then x becomes r. So r makes it 0. If you pick larger than r, that's impossible, and it becomes negative, so it has to be between that. And that is an open interval. Now let's differentiate v prime of x. We want to differentiate pi h times 2x, or 2 pi hx, minus pi h over r times x cubed gives us 3x squared. Okay, so that's the differentiation. And we are going to factor things out here in order to find the values of x that make them 0, because we want to set this equal to 0. And so it's easier to take the pi hx out. If I take this as a common factor, 2 is left here, and over here we get minus 3x over r. Okay, so pi h give one of those x to this one, and we get minus one of x's remains, so minus 3x over r. If you set this one equal to 0, when you set this one equal to 0, either x is 0, either x is 0, or 2 minus 3x over r is 0. So x is either 0 or 2/3 r. And going back to this, it obviously can't be 0. So the only possible answer is 2/3 r. So now we are going to do the first or the second derivative test. So v prime is given. You can go here or here. It's probably here easier to differentiate this because it's 2 pi h. I'll show you the v double prime, and I leave it for you to prove this is negative. So what is v double prime? Two pi hx, 2 pi h minus pi h over r times 3x squared gives us 6x. Okay. And all you have to do, replace the x with 2/3 r, and you can see it's negative. I'm going to leave it for you to prove that. Negative means concave down and maximum. So concave down looking like that. The maximum occurs at x equals 2/3 r. Now, finding the maximum volume, you can put it back into the formula for the volume. Pi h, you can do it here, or you can do it here. You can find the dimensions. Pi h x squared minus pi h over r x cubed. Now replace the x with 2/3 r, and this replace it with 2/3 r. Over here, if you factor the another x, okay, pi h x squared, you get this one. So pi h 2/3 r squared, 1 minus 2/3, and this is obviously four over 9 r squared times 1 minus 2/3, 1/3, 1/3, and you get 4 over 27 pi r squared h. That is the largest possible volume, 4 over 27 pi r squared h. As you can see, some of the questions can be involved, but the process is very straightforward. The next topic is Newton's method. So consider a function as it crosses the x-axis. So that means we are looking for the zeros or roots of the function. For example, in this case, y equals f of x crosses the x-axis is at this point, this point, this point. So what do we do? Newton noticed that tangent line close to the root crosses the x-axis nearby. So, for example, here, as you can see, this is the x-intercept for the tangent line. This is the root we are looking for. And we use y minus y1 equals m times x minus x of 1. This is to find the equation of a tangent line, everybody, okay? So if the first point happens here, so we start from somewhere, we draw a tangent line, okay? And what is the equation of a tangent line? Y minus y1, m times x minus x of 1. So y minus y1, f of x of 1. m f prime of x sub 1, x minus x sub 1. Now, I put this in a red, and I want to show you that if we look at this line, everybody, and if you are interested in finding the x-intercept of a tangent line, that means we are looking for this point, we set y equal to 0. So if I set y equal to 0 here, okay, so you change this to 0. 0 minus f of x sub 1 divided by f prime of x sub 1 becomes this. 0 minus f of x sub 1 divided by this becomes x minus x sub 1. If I move this to the other side, this becomes positive. So x sub 1 minus this, that means f of x sub 1 over f prime of x sub 1 is x. This is the x-intercept for the tangent line, or the new x sub 2 in essence. So use that point as a second and usually better estimate. By the way, sometimes it may not. If the tangent line has a slope and it becomes close to a horizontal tangent line, then it won't work. Okay, has a slope that is close to 0, it won't work. Okay, so we are assuming it gives us a better estimate for the root of the function. So what we do from here, x sub 1, we go to this point, we call it x sub 2. So now this x sub 2 is an approximation that we are looking for. Okay, so this was x sub 1, this point. We draw the line, this is x sub 2. And now this x, we actually call it x sub 2, and we go through the same process. So x sub 2 was equal to x sub 1 minus f of x sub 1 over f prime of x sub 1. It comes from the tangent line, everybody. And if we continue with that, the next one, x sub 3, would be x sub 2 minus f of x sub 2 over f prime of x sub 2. And repeated application of this process is called Newton's method, which gives rise to the general formula. Instead of 2 and 3, we call it x sub n plus 1 is x sub n minus f of x sub n over f prime of x sub n, meaning the next point, n plus 1, refers to the next point. You use the point before that, and you do the process. And to recap this, again, we are looking at the same concept. This is the Newton's formula. Consider a function as it crosses the x-axis. The root, Newton noticed that the tangent line close to that root crosses the x-axis nearby, tangent line intersection. So if you are looking to find this point, this is the root, this is the x-intercept. So you pick somewhere as your starting point and you draw a tangent line. If you call this x sub n, the next one is x sub n plus 1. And this point is the root of the function? No, but it's closer to that. That's the concept. And we keep on getting closer and closer. That's the idea. So if we continue with that, we start from somewhere, we draw the tangent line, brings us here, which is closer to that. So over here at x sub 1, we draw a new tangent line, brings us here, which is closer, and we keep on going with that. So that's the illustration. And I have the also illustration here, which really tells us we are using the equation of a tangent line using the point slope y minus y1 equals n times x minus x sub 1. So you have a point, okay, x sub 1, you draw a tangent line and it gives you x sub 2, and you keep on doing that, and you get closer and closer to the actual root. So you have x sub 1, this is x sub 2, this is x sub 3, this is x sub 4. Just remember the formula. Now, I'll show you a couple of examples that are fairly simple to deal with. However, it can become tedious because it's a pretty long process at some point. So I also give you the calculator program specifically if you want to use a calculator for a more complicated ones for your homework. So you let y1 represent f of x, whatever f of x is. You let y sub 2 represent f prime of x. And then your starting point, wherever you start, number 1, number 2, number 5, number 10,000, you store it. This means store it in x. And then x minus y1 over y sub 2, store it in x. You enter repeatedly, gives you all the answers. I will quickly show you as we go through a couple of examples. So here's an interesting example. We want to calculate 3 iterations of Newton's method to approximate the zero of f of x equals x squared minus 2. And they tell us start with number 1. So we're going to write this formula. So the very first thing is if f of x is this, we need to find f prime of x. According to this formula, we need f of x, we need also f prime. And by the way, as you look at this formula, you can divide by 0. So if f prime is 0, that means you have a tangent line which is horizontal. So if this number is close to 0, the Newton's method will fail. So f of x is x squared minus 2, f prime is 2x. So here's the graph of x. Remember, y equals x squared and bring it down by 2 as far as it's a portion of the graph, okay? And we are interested, for example, in finding this, which is the root or the x-intercept or the zero of the function f of x equals x squared minus 2. We are interested in that. We start at some point, which is x sub 1 equals 1. So at x sub 1 equals 1, which is here, we draw a tangent line. X sub 1 is here, we draw a tangent line. Okay, so I want to make sure we understand exactly what's going on. So this is the tangent. Notice what happens, the tangent line crosses the x-axis at this point. Is this the root? No, but it's pretty close, not too bad. And that one, we call it x sub 2. Okay, and basically x sub 2 equals x sub 1 minus f of x sub 1 over f prime of x sub 1. And so we are going to replace x sub 1 with 1, f of x sub 1 over here. We plug in 1 over here. We plug in 2. So f of 1 minus f prime of 1. And so f of 1, if I plug in 1 here, I get 1 squared minus 2, which is negative 1. If I plug in 1 here, I get 2. So this one is negative 1. This one is 2. This makes it plus 1. 1 and 1/2 gives us 1.5 or 1.5 or 3/2, however you want to put it. We need to do 2 more. So we did only 1. So now this, we're going to call it x sub 3. This, we're going to call it x sub 2, x sub 2, x sub 2. So this is 1.5. Okay. X sub 2 located at 1.5 comma 0. Which means here, which means we draw a new tangent. Notice that it's very hard to show it. This new tangent line, the green one, is even closer to the actual root. So it's almost impossible to show. By the way, we've already blown up the function y equals x squared minus 2 or f of x equals x squared minus 2. So x sub 3, we write the formula for x sub 3. And we are going to replace x sub 2 with 1.5. You should be able to show work at least for a couple of them, okay? And then if you want to use a calculator. So this is 1.5, f of 1.5. So you put 1.5 here. You square it. Minus 2. 1.5 squared is 2.25. Minus 2 is 0.25. over f prime of 1.5. 2 times 1.5 is 3. And the answer is 1.4166667, a bunch of, decimals. As far as the number of decimals, normally they tell you, otherwise use a lot of decimals. And so now we write x sub 4, the same formula. Over here, we change the 2 to 3, which means we are going to, and I hope you realize now, this wasn't too bad, this wasn't too bad. Now this becomes pretty difficult. Now I have to put this number in. So we're going to put this number in. And so you put this number into f of x, you put this number in f prime of x, you do the math, and I'm going to just show you the answer with a bunch of decimals. Again, however many decimals that they ask you. So I hope you realize finding f of x, f prime of x is not difficult. Finding x sub 2 is not difficult either, okay, especially if x sub 1 is nice and easy. And even x sub 3 wasn't too bad, but then it becomes more difficult. And as long as you can show your work for f of x, f prime of x, x sub 2, x sub 3, then it means you understood, and it becomes a fairly simple concept for you. All right, we want to use Newton's method to approximate the 8th root of 500 to 8 decimal places. So using the Newton's method, ultimately, it's very similar to the concept of differential and linearization, okay? But it has a different approach. So what do? You let this one be x, and therefore x to the power of 8 is 500. And so in order to solve this equation, it is the same as finding the zero for a function f of x, which is x to the power of 8 minus 500, or 500 minus x to the power of 8. So all of this is the same as finding the zero or root for this function. So to do that, the formula says we need f of x sub n, we need f prime of x sub n as well. And so f prime is 8 x to the power of 7. So we put this 2 into this equation in general. It's a good practice to do the general and then specifically for x sub 1, x sub 2, x sub 3, and so forth. Because x sub 1 is either a choice that they give you or you choose on your own. All right, so that's the general form. Now, they haven't given us where to begin. You have a choice. And because you can use the calculated program wherever you choose, I mean, if the number is way off and you have to do it by hand, it's very difficult. But with the programming, it's not a big deal. Notice that the 8th root of 256, or 2 to the power of 8 is 256, 3 to the power of 8 is 6,561. So you can start with one of them. It doesn't matter which one. And let's say we start with number 2. And we go until we see the answer agree with how many decimals? 8 decimals. So according to this formula, therefore, x sub 2 is x sub 1 minus x sub 1 to the power of 8 minus 500 over 8 x sub 1 to the power of 7. And we've chosen 2, so we're going to replace the x sub 1 on the right side, each and every one of them, with number 2. Again, since this is doable, you raise this to the power of 8, you subtract 500, you raise this to the power of 7 times 8. And this is 2 minus negative 244 over 1024. This makes it positive, and it gives you the following. If you use a calculator, it gives you this answer. Now, obviously, when you look at this number, you don't want to have to go through the same process again and change x sub 2 now to x sub 3 and change x sub 1 to x sub 2 and plug in this number. It becomes very difficult to do it. And that's why we use the formula. Again, y1 is f of x. So in y1, you put this function x to the power of 8 minus 500. In y2, you put f prime of x, or 8x to the power of 7. then you store x sub 1 in x. We decided to go with 2. So you store 2 in x, and then x minus y1 over y sub 2 stored in x. Repeatedly enter, you have the answer. And so notice what we are going to do. We're going to put 2 into x, and then x minus y1 over y2 in x. And what are those numbers? If you enter it once, you get this number. This is what we have. If you enter again and again, it keeps on going. So where do you stop? They said we want 8 decimals, right? So you look at those numbers until the first 8 are the same. Obviously, these two are not good, these two are not good, and it's getting better. Look at this area and notice, see, 1, 2, 3, 4, 5, 6, 7, 8. 8 of them are identical. Since 8 decimals are identical, this is where you stop. And so you write the answer is 2.1745592. And after 7, we have 6. So you change that. See, this one is not good enough, okay? You do the rounding, and 7 changes to 8. That's how you do the math. I can't emphasize this enough. Use Newton's method to approximate the positive root of this function 3 sine x equals x up to 6 decimals. For a case like this, and again, I have the programming written for you, the formula for Newton, and you have to sort of graph it to know where to start roughly. So this is the graph of y equals 3 sine x. This is the graph of y equals x. And since you want them to be equal, points of intersection, okay, so you want to know those points and what they are. So first, you bring everything to the same side, and you make it a function of x. Whether you go with this one and to the left or this one to the right makes no difference. And this is the point we are interested, by the way, because positive root. We are interested in the positive root. And so f of x is 3 sine x minus x. We need f prime of x, 3 cosine x minus 1. So if I want to write this, it's x sub n, f of x is this, minus f prime of x is this, and we change the x to x sub n. Okay, so x sub n plus 1 is x sub n minus 3 sine x sub n minus x sub n over 3 cosine x sub n minus 1. And just as an example, we have to start from somewhere, okay? X sub 2 is x, so change everything here to x sub 1, x sub 1, x sub 1, x sub 1. And where do we start? I hope you realize this one has a coordinate close to 2. You can start with number 3 or 2. Let's start with number 2, according to the graph. And by 2, we mean 2 radians, okay, everybody? So even with 2, we don't know the answer, so you replace this with 2. So three sine 2 minus 2 over 3 cosine 2 minus 1. And as I mentioned, it's in radians. You put it into a calculator, it gives you this answer. Now, let's take a look at the programming that takes place. First of all, in y1, we put the function f of x, 3 sine x minus x. In y2, we put f prime 3 cosine x minus 1. And then we put number 2 in x. That means we store it in x. Then x minus y1 over y2 over x gives us this answer. And I just went all the way to 2. That's all. Because 1/6 decimals. Then I'm going to repeatedly press enter, enter. So x sub 3, for example, is from here, right? Take a look, and I'm going to start at number 4. And I want to do the rounding. To the right of number 4 is number 8. So I take it 1 notch up to 5. If I click on it again and again, notice what happens. They are the same here. We want how many decimals? 6. So 1, 2, 3, 4, 5, 6. You see this one? 5, 6. Up to the 6 decimals, they are identical. Okay. And so I'm going to stop here. Do I leave it as 2? No. Next to it is 6. Or in this case, next to it is 8. So I change it to 3. X sub 4 and X sub 5 are both equal to this number, rounding. It is important when you round them, they should give you the same answer. Otherwise, it's not. Then you have to go 1 more. And this is the final answer for this. But I want to quickly show you is that if you use a calculator class, first, I want to show you the y. So you put in here f of x, 3 sine x minus x, and then f prime of x, 3 cosine x minus 1. And then you store 2 in x. Okay, I can show you again. 2, store it in x. Enter. Then x minus, I want to go with y1 vars functions y1 divided by functions y sub 2, and I'm gonna store it in x again, and it gives me the number that you see here, which is the same as the number here. If I press enter again, it gives me the next number, so on and so forth. I just wanted you to be exposed to that. So this is how you do the use the calculator for programming.